So this video has somewhat of a grandiose title. I called the playlist "The Beauty of Physical Argument," and I was discussing online on Reddit actually why I'm doing this channel, why I'm making this YouTube video, and someone sort of steered me back in the right direction and sort of reminded me why I'm making this channel. I sort of started out just showing a bunch of derivations that I know how to do, and it's taken me several years to get an intuition for and understand them completely. But I sort of got away from what I wanted to do, and that's what this video and this video series is really about. This video is about the inverse square law, which I'm sure if you're watching this channel you've probably heard of. And what I want to do is I want to demonstrate, well, what the playlist says. I want to demonstrate the beauty of physical argument. I want to demonstrate how you take a set of relatively small postulates and you can derive things like the fact that planets have elliptical orbits. And in this video series, we're going to do that. And I'm going to demonstrate at each point along the way what postulates you need to make that happen. So without further ado, let's jump in. And I can't overstate how important the inverse square law is in physics. We're going to start with light. Okay, imagine you have a light source, and all we know about this light source is that it radiates. It radiates in all directions, and I mean this is obvious. Human experience has shown us that if you have a light bulb, it's going to radiate light in all directions. So I want to get quantitative about this. And there's several ways to do this, and I'm going to do it in a couple ways if I can. I might have to split it up into two videos. But I want to show how that this light can be represented by a field and how that field is related to r, radius r, or the distance away from that source. And let me first say that I think that the canonical way that this is taught is backwards. Often you talk about the inverse square law first, and then you get to flux later. I'm going to talk about flux first because I believe it makes sense. So imagine you have a panel, okay? Imagine you have a panel at some distance r, and I'll just call it r away from that origin. And we'll call it r1, and we will let r1 equal 1 for argument's sake. Well, what if at double the distance, okay? So what if at double the distance I have another panel, and I'll call it R2, okay? And this is twice as far away now. There's another panel back here, but the property of this is that the light envelope, maybe I'll do this in a solid line. The light envelope from the light source comes back here this way, okay? And it's the same on the bottom. And of course, there's a panel back here. And the question I want to pose to you is how much light hits both of these targets? And I think we would all agree that the same amount of light hits, I will call this A1, and this is a cross section. So A1 is sort of the areas into the page, and call this A2. And just for convenience sake, I'll also give us an angle here and call that theta. So what I'm going to do is I'm going to show you that R1 equals 1, and I'm going to say R2 equals twice R1. So R2 equals 2 in this case. So this is a very simplistic example, but I wanted to make it as simple as possible to demonstrate how the inverse square law comes about, and it simply comes about sources that radiate and when you make assumptions about what we're calling the intensity of that source. So what I'm going to say is I'm going to say that there's this amount of light, and I'm going to call that quantity. That quantity I'm going to call phi is the symbol that we use for it, and it's called the flux, and I'm going to call it the intensity of the light for the first one times the area of that panel, A1, and of course we have phi 2 is equal to I2, let me write it up here, and phi 2 is equal to I2A2. I'm going to assert that these two things are equal. I'm going to assert that the amount of light, phi 1, equals phi 2. Okay, which of course implies I1A1 equals I2A2. All right, so getting back to our diagram here, I'm going to demonstrate what L1 is here and compare it with L2. It's a very straightforward, just trigonometric process. If we take tan of theta, okay, tan of theta is going to be L1 over R1. So we can say that L1 equals R1 tan theta. All right, that's pretty easy. Now we can make the exact same argument for L2. L2, because that angle doesn't change, is R2 tan theta. Okay, where we know tan theta is not changing for either of these. So L2 is going to be R2, which is twice R1 times tan theta. Well, that's really just twice times L1. L2 is twice L1. Okay, no surprise there. This is just basic geometry. So let's go ahead and compute. A1, and I'll just do it down here. Try to get it all on one screen. A1 is, of course, going to be equal to. If you think about this area here, it's going to be equal to twice L1 because we got to go this whole length, and we're assuming it's a square, and we'll say it's square, so we get 4L1 squared. Now, what's A2? A2 is going to be twice L2 squared. Well, I just told you that L2 was twice L1, so really we get 4L1 squared, and that gives us 16L1 squared, which is really 4 times A1. A2 is 4 times A1. We can also intuit this, but I wanted to derive it. So if we take our little expression here, phi 1 equals phi 2, okay? If I say phi 1 equals phi 2, when we expand this, we get I1A1 equals I2A2. Well, I just told you what A2 was. I just told you that A2 was 4A1. Cancel these things. And then we notice something here. However I arrange these numbers, as long as this relationship of R2 equals twice R1 holds, what you'll find is that this number here is always R2 squared. And moreover, there's another sort of imaginary number here. I don't mean complex. I mean it's kind of hidden. There's a 1 here, and really this is R1 squared. Okay, so you can devise this however you want. You will always come up with R1 squared I1 equals R2 squared I2. Now, what does this tell us? What does this tell us about how intensity varies with the radius? Well, these are constant. These two things are constant. And if we generalize, I would argue that there's a source here. Okay, I would argue that there's some source. So maybe we'll call our light source S. Maybe it's just the sun, right? So what you can say is I1 is proportional to, I'm going to say some source divided by R1 squared. And of course, this is general for any I, so it's actually I is proportional to the source over the radius squared. And it's just as simple as that. It's deceptively simple. We get I equals some constant. Let's do it in a different color. Let's do white. I equals some constant, and I'll call it KL for light, times the source over R squared. Okay, so this is a bit of a hand-wavy argument, because you might say, well, this seems very contrived. R2 equals R1. Well, in reality, it's not contrived, because what you have is, if you have a source, I'll draw it again. If you have a source that radiates, if you take infinitesimal patch of area here, and then another one at a different radius, Well, what is this? What is this? Assuming you're making some angle. Okay. So assuming this is r and this is some angle theta, the arc length here is r d theta, and of course the area, that area is r squared d theta. So if I'm telling you that the area, let's say area 1, dA1 is r squared d theta, and dA2 is r squared, let's call this, it's still r1 and r2, but the theta is the same for both. Well, we get the exact same thing. We're going to get this intensity I1 dA1 equals I2 dA2. This is a more sort of physically rigorous argument. Okay, this is probably the mathematician's preferred argument to the problem, using spherical coordinates, polar coordinates, and showing that this is true. And from this, you can deduce that you still have to have the inverse square law be true, because of course, what's the area of a section of a circle or a sphere? It goes with r squared. So just as a concluding point here, I'm going to make a point that imagine you have a light source, imagine you have an electron, and imagine you have a mass m. Well, in the light source, I just showed you what the intensity was. I said I is equal to some constant of proportionality times the source over r squared. Well, you may or may not be surprised to know that if you have an electron that emits or has a field associated with it, we get the exact same equation. We get the electric field E is equal to Ke times Q, and in this case, this source charge is plus Q over r squared, where Ke is equal to 1 over 4 pi epsilon naught. And in the case of gravitation, this exact same principle applies. You have some mass, we call it capital M, and well, what do we know about gravity? It's actually a force that points inward, not outward. The exact same reasoning applies, okay? The exact same reasoning can be applied to this system. And what we find is that the acceleration A is going to equal, it's actually going to be negative, and we can get into vectors later, but it's negative some constant, which I'll call capital G, times the source, capital M, over r squared. Okay, guys, so that's my video on the inverse square law. I think when it dawned on me that it can be derived in this really simplistic way, starting with the concept of flux and realizing that this same amount of light is going to hit both of these targets, it's an extraordinarily natural derivation for this intensity, this intense light intensity or electric field or acceleration, which you might think of as the field associated with gravity. But that's it. Don't want to keep it any longer than this. That's one way that you can derive the inverse square law. Please like and comment and subscribe, and let me know what you think.